welcome back to my YouTube channel. Okay, so it's been a few weeks and I have a lot to talk about. As usual, I will do a quick intro into the project that I'm holding in front of you. We have a lovely background today into the field. Okay, so as usual, I will do a quick intro. I will do a full project walk around. I will do a 3D design, modeling, animations, and finishing with the actual manufacturing process. So there's a car passing there, so there's going to be a wee bit of road traffic, so I'll wait till it passes. Okay, so this project piece was built approximately 2 to 3 years ago for my Honda Integra DC5 Type R that I have only recently started again. The engine I have in the car is a 3.2 VTEC V6 engine, so it's a J32A2. They are manufactured in the American market, or California and America. So what else do I have to talk about? So it is evident that this manifold is not only fired together in my workshop in one day. There was a lot of heartache. I don't really want to say the number of hours that was put into it, the whole thing, including design. But in this manifold by itself, try multiplying 60 by 10. It's a lot of hours. This is all handcrafted and all hand polished, and everything's designed and flow simulated, so there's a lot of work in it. So I'm going to now sit this down and take these gloves off, because I've actually got gloves on here, but it's approaching really warm it is. Must be approaching or creeping over 20 degrees. So I'm going to sit this down and finish this introduction off. Okay everybody, I had to go and get a nice pop air starting to cook holding that manifold. Sweat's running down my forehead. Okay, so where do I finish? I'm going to finish with the introduction. I'm going to move. That's not the last I've seen of the manifold. I'm going to do a full walk around now in the manifold. I'm going to weigh the manifold. I'm going to weigh the J32A2 manifold. See the weight differences. I've never done this before because I don't want to mark my manifold. But I have got really good scales. They're really precise. They're calibrated. I don't know what they're calibrated to, but they're really good. So we're going to weigh both manifolds. But I would like to say, before I finish the introduction, at the end in the manufacturing process, I have started to build a CNC TIG welder. That manifold was welded with it when I was in the process of building it. Both the manifold and the welder itself. So you will see the welder in operation and video clips in the manufacturing process at the end of this video. I would also like to say, just like my other projects, this one is quite long because there's so much detail involved in it. It's unique. I believe my projects are by far unique worldwide, and I hope one day that they will be recognised and they will be seen. Not to boost or nothing, but just saying. Hope nobody's walking down the road listening to me there. Okay, so I would just like to say also, this I've already mentioned it, but I'm going to mention it again. There's a very high level of detail in this video, from simulation to animation of the manifold itself, using Computational Fluid Dynamics embedded within SOLIDWORKS 3D CAD. There's a car passing. Breaks for music like me. Okay, so where do I start? So I have simulated air and gas flowing through the design. I have simulated different iterations until the final design. So I'm now going to move on to the actual manifold itself, and I hope you enjoy. Okay, so where do I start? The one's picking up now, so hopefully it's okay here. Okay, so this jewellery like manifold was welded in stages and hand sanded and polished to give it that unique, artistic, creative or original look. Again, like all my projects, this is one off and hand built at home. If this video runs long, please pause and come back another time. I like to keep everything together in my videos. I could have made 10 videos off this project. I'm doing it for my own head as well, showing it off, you know. So if I kept these under blanket and never showed it off, I'd be a wee bit disappointed in years to come, I think. So what I'm going to start doing now is I'm going to start talking through the actual design and why I use these things and stuff. So there are many manifolds. I don't really want to put them up on screen because I don't want to slate nobody else's manifold. So manufacturers have created competition manifolds for engines, but the problem with them is the 6 runners are all unequal lengths, and some of them don't even have runners. They have one plenum on top of it, which is very big and very bulky. So I have designed this manifold so the plenums are separated, much like J32 manifold, only I have done away with the butterfly flaps. Okay, so there are 6 runners, 2 plenums, 1 Y piece. The Y piece is stainless steel, only it's powder coated in candy red. Below the red candy there, you have a white powder to make the candy stand out. We also have 2 barbs for vacuum, for the likes of any, what do you call it, fuel pressure regulator valves and stuff like that, or purge valves. We also have an air temperature sensor in the manifold itself. The V-band clamps are purchased. They are 3 inches. I have coloured them with putting temperature in them. What else is there? So this Y piece, you can see that the radiuses are all quite sharp. And let me see what I mean here. So there's not only one bend here, there's multiple pieces set in to give you this nice tight radius. So the same at this end. This here too, I forgot to mention this here. So this manifold is lifted up here in the end. It's 90mm at the throat, where the intake of the air is. 2 3-inch pipes run into this 90mm hole. However, both of these pipes are flared out, and there's pieces set in. One piece set in here, and all this actual Y piece is actually purged. As you can see, it's all ported and polished, or ported even inside. So there's no welds. However, it is completely welded through as I have purged it with argon gas. What else do I have to talk about? So this manifold is 95% complete. It is currently covered in dust. And that's why I was wearing gloves earlier on, because I don't want to scratch it. So I have to give this a final polish before I start welding it. Obviously the plenums are already fully welded. I have discussed that already. So the plenums is fully welded using my TIG welder on a CNC welding system that I started building the time I was making this manifold. This manifold is currently covered in polish. You can see it here, black polish everywhere. Might be hard to see. So there's black polish on it. If you're wondering what that black stuff is, just can be rubbed off with a sort of special polish. So this manifold needs 12 welds to finish it off at each of the plenums. However, I didn't want to rush that because I'm in the process of buying a new welder. So that's that. So when we move into the solid or the CAD model, you will see this manifold is identical. So obviously I built the CAD model first, and then I built this here second. The flow simulation is really interesting. Please watch it. It's a very nice animation. So I've actually turned the animation into, you could say it's mimicking an engine. So I've mimicked the manifold on an engine and put it through a cycle. So that's that. We'll move on to the flow simulation. But first I will give a wee discussion on to why I removed the butterfly flaps, or the swirl flaps you could call them. Okay, so I brought this inside mainly because it was getting very warm outside, and it's not even that. I'm trying to show off the features of the project better in the shade. Okay, so most J-swap cars have issues with manifold height, so the axle plenums sitting up and hitting the bonnet on cars such as EG Civics, EK Civics, Other things to get. I have this engine on a DC5, so bonnet height is not so much a problem, but the standard J32A2 manifold does hit my bonnet. So that's why I started building the manifold. I have completely done away with the butterfly flap system that's in the J32A2 manifold. On J-swap cars or other cars there is no provision for it, as the J-stock butterfly valve seldom works, or it can stick on various models, and it also adds weight and hurts top end power when the butterfly is non-functional. So moving on, but first I will give a brief intro into the butterfly valve system. So as you can see here, my manifold's designed with 6 runners that are not too long, but they're not short either. Considering manufacturers put the plenum directly on top of the runners that's on the engine. So I have actually extended them a wee bit more, which is similar to what's inside that J32A2 manifold. But I have completely done away with the butterfly system. So I'm going to explain it, or try and explain it. So the intake manifolds come on a J32, and most J-series contain a butterfly type valve that operates according to RPM and also engine load. So there's a servo motor. I could actually go out and show the J32A2 manifold, but I'm not going to bother. So there's a cable and a servo that operates the valve itself. The systems don't allow more air into the combustion chamber like VTEC, but it does alter the air velocity as the air is routed via shorter and longer passages within the manifold. Many car manufacturers have developed variable and twin length inlet manifolds, which change the dimensions of the inlet runners at a certain RPM to give improved torque across the rev range. My interest here was, within my manifold, was to gain torque in the low range. So that's why I have runners that are quite, they're not long, they're not short either. Without getting very technical, the purpose of the valve anyway is to maintain a very smooth and flat power and torque curve. A longer runner length at low RPM increases the air velocities to maximize fuel optimization, and the mixer which gives you more torque. So I have plenums which are not big and which are not small, so I've went middle within everything. Some car or companies or performance companies put one big plenum on the top of their 6 cylinders. However, this 6 cylinder is far away from the port, the float of the throttle body where the throttle body mounts on. So me designing this splits it all up and sort of keeps things in balance. The runners are all, as I've mentioned, are equal, same length. So my interest, as I mentioned, was to increase the torque throughout mainly the low range, but also the high range. So I've designed this manifold to benefit both. So I'll give you an example. So for low end torque at low RPM, you want narrow runners and small plenums. My plenums are medium, so they're not small. So at high end torque, you want these runners short, but you want them wide, and you also want large plenums. So in order to get the right combination, or to get the right balance in the areas, my choice was to go with long equal runners with twin medium sized plenums connected equally at a custom Y piece here. So this Y piece splits the 2 plenums from 1, you could say. This is a common point. This Y piece has the 2 plenums connect straight to it. My design was not easy, considering I sought a manifold that was reduced in height for bonnet space or room even, but also increased in performance. I had other prototype plenums that can be seen in the manufacturing process in the end. So I do show actual plenums that I designed before this one. Other advantages of increased this here manifold, as you can imagine, the plenums are in the centre of the crank, in the centre of the head. And if I've mentioned already, other performance companies create these, I don't want to mention names, but they create these manifolds where the runners are unequal and there's one plenum at the back of the engine. So obviously this is more work involved in it, but it's different. So I should mention too that I'm going a wee bit too much into detail. So the intake volume is the volume of the inlet system, this whole system, all the runners and the plenums. Didn't want to make that huge, I wanted to keep it quite small. I had other prototypes, as I mentioned, with one plenum, which was probably less intake volume. But I just went with this design as an end up. So as you can see from my manifold, I have kept the runners the same length, as I've mentioned numerous times. All my runners are identical within micrometers here, from the inlet port to the face of the head, from here to the plenums and to the common point. So that's really it. So we're going to move on now to the flow simulation. So I'm going to force air in to the manifold. I'm going to mimic firing order and go from there. Okay everyone, I forgot to do two things. I forgot to put my top on during the last video clip, but I'm not recording it again, no chance. So the second thing I forgot to do was show the manifold on the engine. So this is my J32A2 manifold on a J32A2 engine. This can obviously fit all our J series engines, or all J series engines. The throttle body is also mounted, as can be seen here. I don't want to open it because the manifold is only sitting there, but I'll put the stand down, the camera down. So I'm going to open the throttle body, just to show. I don't know why, but I'm going to do it anyway. So here we go. Oh, wrong way. So 90mm. The manifold's only sitting on the engine on top of the runners. So I'm just going to give a wee walk around. So it looks quite, move a stand. Really neat. It'll be nice when I get the engine done up. I'm currently designing stuff for my PhD, so I don't have time to do this at the meantime. So I'm below, forgot to mention, this is a J32. When that manifold's on the engine, you don't see the injectors or the fuel reel. But this engine will be quite nice when I'm finished with it, because you will see the injectors and you will also see the fuel reels. So again, before I move on to flow, I keep saying this, but I keep forgetting to do things. So it's one off. I hope you enjoy the flow simulation. Please watch to the end if possible. Pause and come back other days. I should mention too that you can see the reflection of the runners in the plenums now when the sun's hitting it here up high, and this side, which is really, really nice. Obviously the manifold's just sitting on the... This manifold's going to be put away now because I don't want to destroy it until I get time to... So you can see here the air temperature sensors at the back of the engine, the barbs for the solenoid valve, or purge valves, and also fuel regulators sit about here. So these pipes can be branched off. I should also mention that... I'll just show this, I never showed this. So look how close the plenums come down inside the rocker cover. They come down very close. They within 3 or 5 mil. You can see the nice curve. So the runners now from this length to this point of the head. So you can see the nice steady flow when the engine's running. The video is probably rolling very long now, but it's different and I think I should show it off. I'll get the chair, stand up at the center, and then I will move on to the flow finally. So that's it at this end. So that's it. There's not much more I can say on it. The rocker covers have been selected. I don't know what colour I'm going to do them. This engine's, as people would already know, it's big brake horse. It's a VTEC engine. It's 3 litre, 3.2. Sorry, my head's away with it. The heat's getting to me out here, but it's already it was already put into DC5 8 years ago, and then I started studying. So that's it. I'm going to move on now to the actual flow. Okay, so now that the walk around's done, I'm going to do the heights of both manifolds leading on to the weight. Then I'll move on to the simulation, the flow simulation. So the height of the J32 manifold is 115 millimeters. Okay, so now moving on to measuring my manifold. Okay, so the height of my manifold is 105 millimeters. So there's 10 mil difference in my manifold and the other manifold. Not much, but every little helps. So that's it. We're going to move on to weighing them now. I'm going to start with the J32, then we'll move on to my manifold. Okay, so I have set the scales to 0 with the hook on it. So now holding the J32 in the air, it is currently saying 9 kilograms. So just to prove it's a J32, it's quite heavy. So I'm basically using my 2 hands to hold 9k. Just to bring it back over again to prove. 9. So again, just to prove that the scales is zeroed, I'm now going to hang my manifold onto them. So, oh god. So 7.2 kilograms. So remember, my manifold is dairy pipe, stainless steel, 1.5 mil thick. I'll bring the scales up closer. Take my hand off them. 7.3. My other hand's here. 7.3 kilograms. That really freaked me out there doing that. Okay, so moving on to a more interesting part, I hope. So this is the model of my manifold before I produced anything, obviously, and there were so many iterations to get it up to this actual piece here. So I'm going to talk about every component here as quick as possible. So we have 2 V-band clamps that clamp the Y piece to the plenums. Each of the plenums is reduced from 4" to 3". 76 mil, I think, approx. These everything is stainless, as you see in the image here, as you've seen in the real model. These brackets are also stainless, coloured with high temperature heat, blowtorch. So as you can see here at the face of this manifold, this Y piece, this is where the throttle body bolts onto. This is a wee bit different from the real model, the real piece. This here hole is 90 mil from here to here, but on this model it's only 76, 3" at either side. It isn't cut out to 90 mil, as it would make the model quite difficult at this point here. So this is actually wider in the real model, just at this point where I'm drawing the cursor around here. Just a wee bit more difficult to draw, so I didn't bother drawing it. So these wee boss extrudes, or these wee barbs, is for pipes to be pushed onto, such as vacuum pipes. Also there's an air temperature e-boss which is threaded for the air temperature on this engine. What else? So, oh yeah, so I have the plates took off here. So before I go any further, I'm just going to demonstrate this. So I have 2 plates, plain and mount. So what do you see? Unsuppressed. So here, this is the plates that you see welded on the actual, the real model itself, as I keep calling it. I have suppressed it to show everybody the inside. Obviously I can't cut that open, this plate off in real life, but I could take off the V-band clip or brackets, clamps, but I don't, so I'm just going to demonstrate it here instead. So inside we have velocity stacks or trumpets. They smooth out how the air rushes into the intake at each of the 6 runners. The smoother airflow means more airflow, and more air means more ability to burn fuel, and burning more fuel means more power. Basically, the trumpet shape smooths the flow of the air into the intake, allowing more air possible to flow through the given volume of the intake itself. So it's not hitting the hard face at this point. So rather than eliminating, removing this, so if I suppress this, remove it, if you imagine the air coming in here, it would be hitting the face and it wouldn't be being directed in. So the air is not hitting the hard face of the plenums on the inside, creating turbulence at this point. So they actually work because I have simulated it, the airflow. I'm going to demonstrate that in a wee while, but first of all I'm going to finish off talking about this. So as at the bottom here we have a 6mm stainless steel plate. Each of these runners is connected or welded directly to it. Everything that you see in the image here, apart from this candy red Y piece, is mirror polished by hand, as seen in the real model again. That's about it. So we're going to move on now to the actual flow simulation and see how we get on from there. Hopefully I haven't missed anything. Oh, one other thing. See here, these wee cutouts. These are actually concave, so they're actually reversed in real life. The real model. They're just welded in the other way around. Just don't think it really made a difference, but I just in the model here I put them on like this. So if you look at it here, you can see it sticking out the way rather than in the way. The same as opposite to the real life piece or manifold. So we are now going to move on and see how the flow simulations get on, and that's it. Okay, so moving on to the simulation or the flow analysis, but first I should give a wee brief description on the fluid mathematical calculations. So the fluid mathematical calculations were set up by the Computational Fluid Dynamics method using the defined geometry that I have created from early models to this model. So I have examined at each point, and I have examined at each point where the air entry to the manifold ports and down the runners to see if there's any noise or turbulence. So each of these parts is enhanced to allow better flow. So these were performed about the simulation of the fluid pressure field, the velocity field, the flow field, and also the local field in the manifold, which led to this final prototype. The results at each of the 6 runners, so here, at each of these points, relies on the geometry, the parameters throughout the design of the intake manifold. Reverse technology is reasonable for the intake manifold design through the theory and simulation analysis. It can ensure sufficient air intake and reduce intake resistance and the energy loss of the air, and can improve the air intake consistency. So I have narrowed any discrepancies using this analysis process. I should point out here, so when you watch the flow analysis, you will see the pressure hitting this face hard, just what I'm talking about there. This is probably the hardest hit place because of the air's been divided into two banks. So I have mimicked, before I go any further, I have to make this model watertight. So to do that, I have created multiple lids, as you can see me pressing them here. So underneath here now, there's all the lids appeared, so I have unsuppressed them. I also have to put the 2 caps back on, the plenums. These is actually welded on, so what do you see here? Plenum cap mount, that's what you call it. So that one is on, and that one is also on. So, what else? Oh yeah, so we have to block off the throttle body port. We have to block off these vacuum pipes or ports, and also this air temperature threaded boss. So if I unsuppress these, this manifold now is watertight. So if I was to fill it with water, there'd be no leaks. Obviously it's not welded here, but there's no gaps around any of these lines. It is all tight geometry. There's mates. These plates is all held in place with mates. They're obviously not welded here. But there's no gaps at all. So now I'm going to run the simulation. I'm going to run the proper firing order off the engine this manifold is designed for, which is, what is it again? 142536. So I have made or created a set of data which fires or sucks a large volume of air through each of these runners. This throttle body port is open to the atmosphere, and I will demonstrate that in a wee minute. So I've set a pressure here in pascals, and here we have there's a volume flow going down here at meters cubed per second, and I think it is, I'm not sure, we'll see in a wee minute, but I have peaked this manifold at 7,500 RPM, so you will see the air. I have obviously, for the purpose of this demonstration, one cycle is set to I think it's 20 milliseconds, so 0.02. But I have extended this to 10 seconds, a simulation, to show the actual manifold in operation, because you would not be able to see 0.02 or 20 milliseconds on the software. So you will see this manifold drawn in by the firing order. So I'm going to demonstrate that now before I start talking more. Okay, so I'm going to run this animation now. I'm not going to go into detail on how I performed the flow analysis or how to use the software, because the video is based on showing off my manifold. So I'm going to run the flow analysis now, and so I'm going to show the firing order. So here's a firing order here on the left, 142536. So it'll fire from this cylinder to this one, to this one, to this one, to this one, to this one. So it'll keep firing bank to bank. I'm going to set it up here now, and first of all I have to, obviously you won't be able to see through it, so I'm turning the whole assembly transparent so you can see through here now. So these yellow plates that I have attached on here, a throttle body and the ports, the bottom of the runners, going into both heads. These yellow plates have specific parameters set on them. I'll try and display them here. So if I go here, so I'll display this one. So it should be displayed there now, but it's not. Show all. Now they'll come up in a wee minute. So there's this. So these there they are now when I click on them. So here we have the environmental pressure here at this point. So this is open to the atmosphere. There's no throttle body on there at all. So basically what I'm mimicking here is the engine sucking a large volume of air in on each downstroke or intake of the 4-stroke engine. So we have time dependent. So I already have these set up. So I'm going to go into it and just show. So I have created a data set here with 6 pulses. So this is firing on the first cylinder. This is firing on the 4th cylinder. This one's firing on the, what is it? Let's see the firing order here. So this pulse is firing on the 2nd. So I'm just going to open up the 4th just to show what I'm talking about here. So the 4th here is time dependent too, within the 20 milliseconds. If I go into the function here, so this is firing on the 2nd pulse, the 4th cylinder. I have it set up here, you see the firing order. So 1 comes first, this cylinder comes 2nd, this cylinder comes 3rd, this cylinder, so it keeps firing from bank to bank as I mentioned. So I'm going to run this now, this animation, and what do we see here? if I insert an animation, I'm going to set it up for, I'll set it to 1 second, and then I'll set it to half a second, just to show the demonstration of it working. So scenario, so basically what I'm doing here is I'm loading 50 results together. I have already set that when I've run it the first time. So that's okay to run there now. So I have to then create a control point. So basically, so if I run this now, it should run. There we go. So the first time it started like rendering, you could say. It's calculating. It's making calculations. So the first time it'll run slow. You can see the rebound there. I'll explain that in a minute when this analysis is over. So when the valve's shut, you can see the deflection or reflection behind even there, this front bank. So that's normal. What do we see? It's going to be a wee bit faster when it finishes the cycle. Oh, it'll be far faster. So it's nearly finished the cycle now. It's on its last cylinder. So, or last stroke. So if I run this now, there we go. So if I remove these, I'm going to stop this for a minute. So if I remove these out of the way, so we can see what's going on here. I don't know why they appeared, right? And I'll take this one away too. No call for it there. So we're going to run this now, again on loop. So first under fourth, what is it again? Second. You can see there anyway. So I'm going to speed it up now. Just going to let it run a wee minute. You see the rebound at the end here. So basically it's crashing against the valves. When the valve's shut, this blue, what do you see? Wait till it comes around this first under. Blue, so it's crashing. When it shuts, you can see the rebound, reflection. So I'm going to move on and set it a wee bit higher here. Faster pace. Okay, so what I'm going to do here is I'm going to speed the whole process up. I'm going to half the time from 1 second to half a second, and demonstrate how the manifold or what the animation looks like then. So that is 1 second. I'm going to stop it here now and change it. Actually, I'll change it to 4/10 of a second instead, just to see how the animation looks. You don't need to rotate the model. We need a scenario. Give a wee description about what's going on here too. So finish that. So I've now moved it to 4/10 of a second. So I'm going to run the animation now and give a wee description about what's going on. So hopefully this looks okay. It looks good. Okay, so I'm going to explain this in more detail, in finer detail. So you can see here by the colours, the blue left behind, so I'll explain it here. In finer detail, the opening of an inlet valve causes low pressure at the engine end of the runner. As the engine sucks air out of the runner, air starts to flow down the runner, seen in the yellow there, from each plenum into the cylinder until the valve shuts, at which point all air travelling at high speed crashes into the shut valves and in turn creates a relatively high pressure slug of air. So that's the scene in the blue there at each of the finishing points. So across the runners there you can see when the valve shuts, the blue appears, so that's the air crashing into the valves basically. So this is reflected and starts to move back up the runner until the valve opens again, at which point it heads back towards the port or into the cylinder. If the dimensions of the runner are calculated well, the high pressure slug or pressure wave will make its way through the port before the valve shuts again, when the next slug is created. Wide inlet runners move the torque curve up the rev rate, hence my design here. So I have them set at 50 mil, whereas narrow runners move the curve down the rev range. But there's a whole lot more to it than that. The effect is caused by pulse waves, waves of relatively high and low pressure in the runner. So what I'm going to do here now is I'm actually going to stop it again, and I'm going to increase it to 0.2 just for demonstration purposes of this video. So I'm going to delete all existing tracks of 0.4. So now this may crash, so I just have to be very slow with everything. Okay, so you can see I have to create a control point now. So I'll create the control point, and I have to take this down to 0.2 without touching other things. So you can see here, we're very the time scale here, like I don't have much left, so I'm going to run it and see what happens here. Okay, so it's running okay. I don't want to increase it any more than that because the computer will probably crash. Right, so I'm going to stop it in 2 seconds because the computer might crash. So as you can see, it's nowhere near operating speed of the engine, but it's for animation purposes. Looks really good. So the blue left behind here is the valves closing and the slug of air that's left behind. You don't want these runners too long at high RPM for that reason. But I will go into that in more detail maybe, or I might just move on now to a flow. So that's it. We'll move on now and put a steady flow through the... We'll force air into the throttle body and open the ports and see how the flow reacts in the chambers or inside the plenums and the runners themselves. Okay, I should point out before going any further, I'll move on to the flow analysis. So basically I'm just going to force high velocity of flow of air through this Y piece. But before that, I should mention the dimensions of this manifold are critical to the operating speed of the engine. All the testing has been, with the firing order, was set at 7,500 RPM. If the runner is short, so if these runners are short, the reflected pulse might fall out of the end before the valve opens to suck it back in. So if the runner is too long, the larger mass of air may react too slowly to perform at higher engine speeds or higher RPM. Such as Formula 1 cars, you wouldn't want these runners too long. So it's difficult to design an engine intake manifold in a normal method because of the complex structure. There's a lot going on, and the real situation of fluid movement in the manifold cannot be obtained through steady flow tests. So the optimized design is proposed about the engine intake manifold based on reverse engineering or multiple iterations that I have completed. So before we move on to the flow test, I'm just going to do one last thing. I'm going to do a cut plot. I'm just going to slice the top of this manifold. So I just want to show you how I've done that. So basically I've set a cut, I put a plane, referenced it off this bottom base plate, and I've took the top clean off this manifold. I will demonstrate that now here. So I'm back onto flow simulation and I'm going to run this. I have it set up. The speed it runs at for simulation purposes here now is back to 0.4 seconds, half a second nearly. So I'm going to run this now. So you can see that there's a nice even flow of velocity of air. It's evenly. That's my wee with arrow over top it. It's well balanced. The colors are well balanced and the velocity between each runner. So that's it. We're now going to move on to a flow test, and you will also see a nice visualization or a nice animation of the flow flowing in and flowing out through the 6 ports, and seeing where high velocity and any errors or any interference or anything like that occurs. So okay, so before we finish up with this flow analysis, I'm going to simulate or animate a flow with a velocity of 25 meters per second, entering this Y piece or inlet where the throttle body should be bolted onto, or will be bolted onto in real life, the real model, and it will simulate the air flowing in, but forced in even, and out the 6 ports. You can see here these tags is stating, well, we know this one's inlet velocity at the intake, but on the output of the runners, the outlet, You can see they're all set to environmental pressure now. So these plates, even though they're there, there's parameters on them to say they're open to the environment. This is basically just to monitor the fluid or the air running down through them. You can use these goals, but I'm not going to go into that. So what I'm going to do now is I'm going to run this simulation, but first I'm going to just show what is actually going to be flowing down here. So I have a, what do you call it, theres. I could set this to pipes, lines, but I'm going to set it to theres for this animation, much clearer. There's 200 points at this face. The more points, the more balls, and more theres you'll see. So I'm going to their size of this, which is very, very small. I could set them bigger, but I've set them small. What's with 4mm? So now what I'm going to do is I'm going to run it here, and okay, so it's already started running now. So I'm going to run it here now. So there we go. So you can see there's a nice steady flow of fluid or air. What we're looking for here is to see if there's any interference. But it looks to be quite balanced and quite even. The velocity down the 4 runners looks identical, which is surprising because, well, it's not surprising because usually the first runner and the last runner be a wee bit of difference in them, but it doesn't look that bad. The manifold is well designed. So here you can see a wee lock of outliers at the first runner, running around that's actually running around the trumpet, or the velocity stack. So if this velocity stack was buried into the plate itself, if it was a milled piece of aluminium, it would probably be better. But this manifold was not only designed for performance, it was designed for looks, and that's why it's made in 316 Mer grade. So what I'm going to do here now is just scroll around to get a look at the other end of it. So there's the underside of it. You can see the flows. They're quite balanced. So you can see here, this Y piece, it's orangey yellow and orangey yellow here. So the velocity here is the same as here. The velocity of this runner is very similar to here, and velocity here is very similar to here. So these runners are not exactly open together. There's obviously a wee delay between them. So what I have already demonstrated in the past clip. So just to clear up here, so this final flow analysis was run with all 6 ports set to environmental pressure, meaning open to the atmosphere. Flow of air was forced, or is forced, down the entry of the manifold where a throttle body would be situated in the real piece. The flow was set to 25 meters per second. A steady and balanced stream of fluid is seen throughout both plenums and all ports by the uniform colours. A small portion of outliers is seen here at the rear end. At low pressure are seen at the nose of the plenum. That's really it. So I might run another cut plot. Okay, so I'm all set up and ready to go here. So air has now been forced into the same animation, only I've cut the model in half and added the cut plot. So you can see there's a nice steady flow of air, consistent flow of air through the manifold and the runners. Wee flaws here, but nothing major, which will be normal. It's just due to the sharp edges and the bends. The air flowing around it at a high velocity. So that's it. Moving on now to manufacturing process. Okay, so before we move on to the manufacturing process, I'm going to demonstrate the rendering of the 3D model, or show images of it. There is 5 or 6 or maybe 8. So these aren't actually photos, these are rendered 3D CAD models, or my CAD model, the assembly. So I knew what the manifold was going to look like before I actually made it. You can see it's quite identical. Couple of wee changes here and there, but nothing major. So this is actually a cut flat. You can see inside it. Another cut flat. Obviously I don't have a powder coated in the inside. So this is an early prototype. Well, this is the standard manifold on the J32A2. You can see they're quite clumsy. So this is my early prototype manifold. It was just going to be one plenum on top of the 6 runners. So I never actually made this, but I prototyped it up on a cardboard as just another template. It was never modelled on CAD. However, I didn't like it because it was tall and there was no runners there for low down torque, stuff like that. Didn't want to. I wanted the runners a wee bit longer. It's just a bad design. But you've got to start somewhere. So this is the engine in my DC5. Not going to go into detail on the car, I'm just sticking to the manifold at the meantime. So that's the plenum or the throttle body bolts on. So this is the same throttle body, 90mm. Skunk 2, I've never mentioned that yet at all. The manufacturer or the maker is Skunk 2. Okay, so now on to making the actual manifold in this video. So first of all, I started with the plenums and just started laying things out, working off the CAD model. So these plates is a lower plate and the 2 plenum plates. The trumpets or the velocity stacks were welded directly to the plenum back plates. So these plenums is made out of 4-inch stainless steel 316 pipe. Tube, dairy pipe even. So this is the velocity stacks welded on. So this is ready for polishing. So still this is welded here. So still working off the model right through this, keeping everything exactly the same to match how well the flows analysis performed. So this is 2-inch runners, 2-inch wide. So the 2 plenums were tacked together and they were polished before they were welded. Sanded all the grain. So these dairy pipe have grain in it, and I sanded the grain out through different stages before I started burnishing it. So burnishing is really using soap, polishing bars up to, I think it reaches temperature 600 degrees. You will see me now performing a demonstration that was recorded 3 years ago off my phone. So this is a cap for the side of the plenum. So the plenum then needed cut to match that cap. So that's basically at the nose of that plenum is to direct air sort of until the last runner, you could say. So these 6 runners was polished before they were tacked in position. So now there's going to be a demonstration of plenum polishing. So a salsa oil they start off with on black bar polish. So you see the effort that they put in to do this. Keeping in mind that this plenum is sanded with a dual action sander before I start polishing to remove any deep scratches. So when I am polishing this now, it obviously gets quite hot. You want to get it polished first. You want to remove all the scratches at the very beginning, because if you polish over the top of the scratches and you try and sand them scratches, and later after polishing it the first time, the scratches are very hard to remove, and laying it is also very hard to polish up again after you sand it. So you sort of work harden the stainless, the material. So what I'm doing here is I'm going back and forward, but also I'm going, you can see the wheel, I'm hitting the wheel diagonally in both directions. So I'm not just running it along straight, I'm doing a diagonal, and then I turn the plenum. I'll do it in a minute. So working my way right round the whole plenum. I think it's, what is it, 300 degrees. From top to bottom. So you can see there now, even it's starting to come up to a more finish. However, after this stage, they also used cloth and final cotton grade soap, which is green, pink for stainless. And after this is polished, I then weld the manifold, or the plenum even. So you can see it's still all lines. A lot of work to polish this up to the standard at the minute. I can see there on my polisher I have a bit of drain pipe, and that's just to cover the shaft, because sometimes you can slip off and hit the shaft and you're on a whole handle then. You leave the stainless all marked. You've already sort of work hardened it. I don't know if it work hardens it, but the top surface becomes very hard to work with once you polish it. So I'm now in the underside. That's it. So at this stage I'm welding on the reducers from 4 inch to 3 inch. Then there's a wee piece cut out of it to match the model, the 3D model. This here. So in the model, this is I think it's convex, and on the real project, the real manifold, it's concave, so it's facing in the way. In the model I have it drawn convex because it was much easier, but the dimensions are all exactly the same. So that cardboard's just a template for the wee piece of metal that I needed to set in there. Just keep it in mind too, this manifold is completely purged on the inside. As the tape's on there to watch I don't scratch the bird up the tip of the pipe. So the plenum welding, I have welded. This plenum was welded in stages, so it's so I've welded it, I've sanded it, polished it, welded, sanded it, polished it, back and forward, a lot of heartache. But in doing that, that's why this manifold looks the way it does. So at this point I have made a welder. Well, I haven't made a welder, I've made like a CNC. I'm making a CNC welder, TIG welder. At the minute I've only got it working on one axis, and I'm adding another axis and see how it performs. It might be a project, it might be a project, but it worked well here now. And I thought I should put this wee clip in just to demonstrate it working, so you can see the nice clean weld. So basically what I'm doing here is fusing metals, two sheets together. So that's it. That's the final weld. So there's 4 welds like this, and after that I could sand these and polish them then again. But it was much easier because you're working off an edge this time. I already have the surface all polished and the grain removed. It should say that both faces, the face with 3 holes in it and the round pipe or tube, was completely polished before I welded it to make things a lot easier. So this is then finished, nearly, ready for final polishing. They still need a wee final polish yet before I put the manifold on the engine, but I'll do that in time. So the runners then, the next stage was to polish these runners. There's 6 of them, exactly the same way I polished the plenum. So you can say, why am I doing all this work into a manifold? Well, I like to be different, and I like to make things different and unique. If you go back and look at all my projects, I go overboard. I enjoy it, so I just do it. So this is the top manifold and nearly all complete. Ready for the Y piece to link these together. So keeping in mind, this Y piece is offset. As you can see, these runners are all the same length. And so obviously cylinder 1 and cylinder 4 is a step between them on both banks, engine bank. Front head and back head. So there's going to be a little, so at the front of these two plenums there's going to be a different distance. So I think it's about 60mm between the two faces, from one throat to the other. So I had to take that out of it with the Y piece that I have made, stainless Y piece. So inside here you can see the velocity stacks. They work quite well. I've simulated it without them and with them, and you can see that the air is smooth, much cleaner put into the runners, been forced in. So this is just a manifold covered in water droplets after I washed the polish of it with hot water. So now moving on to the Y neck design. So this was actually a quite complex part. So started off with 3" bends. There's grain in these bends running around, so I had to sand them all out. But first I have to make the manifold. So this is me making it. These two pieces, which are still being cut, and they are flared and worked in the position of that 90mm hole onto that flange, and you're obviously going to be left with 2 wee holes. So this is hand shaped and tampered out with a rubber mallet and bits of blocks of timber. No, you don't want to use steel against the stainless, because you have to sand cleavages or wee holes out that you beat into the metal or into the stainless. So stainless is quite soft. So this is me setting it up at this particular minute. So I know looking at this I need sharp radius to link these together. But also I just didn't want to weld together one piece. I wanted to be able to disconnect this to look into the manifold, or maybe to look at the velocity stacks or the trumpets. There's the bit shaded that needs to be cut out. So you can see here that I've worked it as far as possible until 90 degrees. Keeping in mind it's 3" tube here, so 76mm, so there's a lot of work to beat this out close, so you're not going to get a ticket out full. So this is the ends being cut into pieces. A lot of work on this, getting it on the nice sharp radius. Now you can see they're all numbered here because I don't know why I numbered them again at the time. So 1 belongs to 2 and 2 belongs to 3. So this is the Y piece. You can see here I used the tape and the marker to get everything spot on where it needs to be. See, I taped it because it was sitting beside the manifold, and I didn't want to. The manifold was in the house at this stage, the plenums and stuff. So this is it coming together. You can see the nice sharp radius. This is all tacked, and that's actually welded on the inside with a tag there. So you can see now what the numbers is for 1, 2, 3. There's no gaps. This is all filed, hand filed. There's no saw used here, and it's hot with a grinder and shaped with file, a flat file. You can see there now the 2 cutouts, how close I've brought the 2 bends to 90 degrees. On the horizontal, and then at the vertical, I have to add in 2 dome pieces. These dome pieces is either where's my dog? So I don't know for the dome pieces. See A's to A and B's to B. So it's coming together there right now. A lot of work in this. I enjoy it, and that's it with the flange tacked on. So when this was all tacked together, there's the wee piece there, was hand cut and filed. So that's off of 3" pipe. You can see there where the one at the top needs to tamp the way out. There now, it's all tacked up. light tax so you don't contaminate the stainless on the inside, because it's going to be purged. I think I have. So there's it now with the top piece set in. So getting this as accurate as this with one piece is really good. You know, it's not easy doing this because stainless is very hard to work with. One of the hardest metals, if not the hardest. It pulls with weld and distorts and it can bind and everything. Stainless is quite difficult. It pulls a lot. So there's A and B. I think I'm working on the other side now. So there you go. So after this, I purged the manifold or the Y piece. Weld completely on the inside. And the outside is sanded. So the reason I purged it is because if I wasn't to purge this and I was to start sanding these welds to bring it up to a mirror, I would obviously meet the gap. So the reason it's purged is so I won't meet the gap and I won't when I'm polishing it in the mirror. So you don't end up in any handlings down the line. Plus it allows better flow on the inside. So this manifold was ported and polished. Still not finished on the inside, this Y piece, but there, so that's me putting argon through it. See the yellow pipe going down through the bench, up through the bench even. The two weights is holding, I think it's a 4.5 inch cutting disc on the face, and there's tape over the hole with wee pins in it. So this is it welded. This part's welded anyway, and you can see it's actually quite good. I tested it, purged. You can see it's welded on the inside there. That's all the pieces welded too, purged on the inside. So this now allows me to be able to grind this and port it and polish it without meeting the other side or meeting any cracks. So you can see how sharp this radius is. There's 3 pieces set in there just to get that sharp radius to match the plenums. This is me starting to port it or grind the welds. This is me sanding the outside of it. You can see how neat I get it. Considering there's so many pieces I've set in there, 6 or 7, 8 different pieces I think. So this is me grinded and ported inside the welds. I have got it really good. So this piece alone here, I don't know the many hours went into this. You can see by looking at it, there's a serious amount of hours went into it. So that's the V-band clips, and that's the manifold nearly finished, ready for powder coating the Y piece. Then V clamps were coloured with high temperature blowtorch. So this manifold now, as you've seen it in the very first clip of this video, is 95, or I'd say more, 99% finished, considering the hours went into it. I should point out again that this manifold here, the practical side of it probably took, scared talking about it, maybe you can see how much work went into it. I'd say about 600 hours. You can see it in it when you're looking at it. The design, the software, the flow and animation, the flow animation itself took maybe 7 days to get it working the way I wanted to get it working. The SOLIDWORKS model, calculations and stuff, and different prototypes. The time, so much. So much time. So this is me welding the boss jetted piece and the 2 barb on for wee pipes for the vacuum, for purge valves, and also fuel regulators and stuff. So the air temperature sensors off a standard J32A2 manifold. This now is ready for powder coating. You can see there we ported inside. These V-band clamps were welded on, all tacked to keep them from pulling. This is them welded, hanging in the oven, or sorry, the powder coating booth that I have in my YouTube videos. The powder, so it's powder coated white first, gloss white, and then a red candies put over the top of it, and then a wee skim of polyester lacquer, powder lacquer. So you can see it looks quite well, and that's it, nearly finished. That's it. So that's ready to be clamped on to the 2 plenums with the V-band clamps. the work on that piece alone, serious. I wouldn't, so the whole thing, 600 there just being nice, I think. So, thank you very much for watching. I hope you enjoyed. Please come back for more videos, and they will be unique worldwide, I promise. One day I hope people will recognize these videos across YouTube and see difference. Please come back. The next video is going to be really interesting and one of a kind worldwide. Please subscribe and like. Not very many people are doing it, but I don't really care as long as I get my projects out there. But if you want to see more projects as unique as this one, please subscribe and like. Thank you very much for watching, everybody. Bye bye.